Hi folks. Today I want to start on a new topic in linear programming. This is a personal enthusiasm of mine. I'm kind of fascinated by games and mathematical games and mathematical strategies for playing games. So I want to show how you can apply linear programming to the theory of games. This is a particular type of game. In particular, I'm going to be talking about two-person zero-sum games. Okay, so games that only involve two people. A lot of games are like that: chess, checkers. A lot of games can be played by only two people, like poker and gin. That's not unusual. The zero-sum part. Well, actually, that's also typical of most kind of casual games that people play. That there's a winner and there's a loser. Both players can't win. And more precisely, a zero-sum game is a game in which whatever one player wins comes from the other player. So one player's winnings is equal to the other player's losings. Right, so that it's called a zero-sum game because all in all, no money is gained or lost. Right, it's just money flows from one person to the other. Right. Of course, you don't have to necessarily think about the payoff of a game as being in money. It can be in other things. It could just be, bragging rights. You get to claim that you won, and the other person has to admit that he lost. But the point is that whatever one person wins, the other one loses. As I said, most games are zero-sum game. Most games that people are familiar with, right? Like in chess and checkers, one player wins, the other player loses. I guess occasionally you can have a draw in those games, and then nobody wins anything, so it's still zero-sum. Betting is an example of a game in which you have a winner and a loser, right? You bet against somebody else, and one of you pays the other one at the end, right? Well, when you settle up, one of you has to pay the other one, and whatever one person won came from the other player. Poker is a betting game that works that way. Sports, in a sense, are zero-sum games because, again, when one team wins, the other loses. There are important examples, though, of non-zero-sum games, and typically they come from economics and from wider society. But there are increasingly in the game world, there are what are called cooperative games, where you can have where the players all cooperate to try to defeat the system. Right. A good example of this, some of you may have heard of this, is a game called Pandemic, where the players all try to cooperate in order to eliminate 4 diseases that are spreading throughout the world. Right, so the players win if they succeed in driving all the diseases out of existence, and the players all lose together if they fail to do that. Right. So cooperative games like that are not zero-sum games. That's a different kind of animal. Also, in economics, a lot of situations in economics are actually, can be regarded as non-zero-sum games, where both parties or all parties, there might be more than 2 parties involved, can gain. For example, if you buy something at a store, you give up your money, but in return you get some product that you wanted, right? So in some sense, both parties can be said to gain from that transaction. Presumably you valued the product that you bought more than the money you gave away, and vice versa. The store wanted the money and was happy to part with the product, so both participants gained from that. And there are other examples, like insurance is a case where everybody pays into a pool, but in some sense everybody benefits because everybody knows they're protected in the event of disaster. And in general, society at large is kind of predicated on the assumption that if we pool our resources, then we share our risks, and everybody benefits from that, right? However, we're going to be talking about the cutthroat species of game called zero-sum games, where there's always winners and losers, and the net generation of money is zero, right? Whatever one person wins came out of somebody else's pocket. Also, I should say that a game, for our purposes here, it's not necessarily the kind of thing you normally think of as a game. It can be any interaction in which each player or each participant picks a strategy unknown to the others, right? So basically, everybody is independently picking their own strategy. They don't necessarily coordinate their strategies with other people, although that can also be involved in game, but it's not necessary. And it's the combination of strategies that everyone plays that determines how much each player gets paid off in the end. So if we have a two-person game, then you can easily represent this kind of situation, this kind of interaction where you have payoffs to each player by what's called a payoff matrix, right? So a payoff matrix is this kind of guy here, where the rows represent which strategy the row player, we'll call him the row player. You can think of him as player one, or the row player, or the left player, and then the other player would be the column player, or the player B, or the right player, or the upper player, or something. But anyway, there are two players. That one player gets to pick which row he wants to use, and the other player gets to pick which column he wants to use. Then the combination of row and column determines the payoff, and by convention here, I'm giving the payoff in terms of the from the point of view of the row player. So, for example, if the row player chooses row 1, so the row player is playing here. Oh, I don't think I can highlight that. Okay. If the row player is playing there, right, in here, and the column player chooses column 2 here, well then, together they've chosen this entry here, the 2, because that's in the first row and second column. So by choosing that, the outcome is that the payoff to the first player is 2. And since this is a zero-sum game, it's implied that those $2, or whatever the units of the payoff are, come from the column player. So row player plays first row, column player plays the second row, and the outcome is that the column player has to play 2 units of money or whatever to the row player. Okay, so very convenient way of describing a game. You really, with this understanding, all you need to describe the game is a matrix. Now, typically, in any kind of realistic game, the matrix would be huge because there are hundreds of moves you could play. Like in chess, for example, this would literally be this matrix would literally have astronomical dimensions, because what you'd have to do is you would have to anticipate all possible strategies a person could use in playing chess, right? Well, all possible strategies that could be used in chess, I mean, that's just not a fathomable number. It's just astronomical, right? So in chess, the payoff matrix would literally be astronomical in size. So we're going to restrict ourselves to more manageable games where each player has only a couple things they could do. Like maybe at most, maybe 3 or 4 things that they could do. And in that case, the payoff matrix could easily be laid out this way, and it could easily be understood and even computed with. And we'll show how to actually determine the optimal strategies for playing a game. Okay, so here are some simple examples that you probably have all played. Rock, paper, scissors, right? That's a simple game, but it's a pretty good example of a zero-sum two-person game. Very simple. Each player throws out your hand in the shape of a rock, a fist, or paper, a flat, or scissors, right? Your index and middle finger are separated like scissors. And the way it works is rock beats scissors, rock smashes scissors, scissors cuts paper, and paper covers rock. So each one of those 3 things beats one of the others and loses to one of the others. If if both players play the same thing, it's a draw. So I'm going to call the payoffs here 1 if the row player wins, -1 if the row player loses, meaning the column player wins, and 0 if it's a draw. Okay. Okay, so here's the matrix, right? The payoff matrix here. So, for example, if the row player plays paper and the column player plays rock, then they'd be in this point on the matrix. and paper covers rock, so therefore the row player wins, and we denote that by a payoff of 1, right? So the row player gets a payoff of positive 1. Notice that this matrix is anti-symmetric. When you reflect the matrix about the main diagonal here, the numbers change sign, right? So we can say this symbolically, that P sub ij, the entry in the ij position, the ith row and jth column, is equal to the negative of the entry in the jth row and ith column, right? And the fact that this matrix is symmetric, or anti-symmetric, I should say, corresponds to the fact that this is a perfectly fair game. In fact, it's perfectly symmetrical. The rules are exactly the same for both players, and the payoffs work exactly the same way for both players. So if the players reverse their moves, then the payoff will also be reversed. That's what this anti-symmetric property is showing, right? If the players reverse their moves, the payoffs are reversed, and that shows that the game is fair, right? It works exactly the same way for both players. Now, because this game is fair, in the long run, if both players know what they're doing, if both players are competent rock, paper, scissors players, we would not expect either player to win more than the other in the long run. So if they're actually betting $1 on each play of the game, then in the long run we wouldn't expect either player to really make any money, right? Because it's a perfectly fair game. There's no reason one player would win more often than the other. So we say in this case that the expected value of the game to the row player, because that's we're always giving payoffs in reference to the row player, just by convention, is 0, right? So the fact that the expected value of the game is 0 shows that the game is 0. That the game is fair. Now, you can have a fair game that's not symmetric, where the payoff matrix is not anti-symmetric. Right? That would mean that the rules seem to be different for the two players, but actually, on average, neither player is expected to win more than the other, and therefore you could still say the game is fair, even though it's not a perfectly symmetric game. Right? The rules are not the same for both players. So that can happen. Let's see, another game of this type. I guess it's even simpler. Maybe I should have done this one first. Odds and evens, or evens and odds. This game goes under different names in different parts of the country and at different decades, I think. It was often used as a way to resolve petty disputes or questions about which player should go first or which team should go first. What you do is two people, like for example, if you're playing touch football, one person from each team would play this game in order to determine who gets to kick off or who gets to receive first, something like that, right? And the way it works is one player calls evens, they're going to be the even player, the other player calls odds, he's going to be the odd player. Then simultaneously each player throws out either one or two fingers. And the sum of the fingers, that is the evenness or oddness of the sum of the two fingers, determines which player wins. So, here's the payoff matrix, right? Again, I'm just going to denote the payoffs by positive 1 if the row player wins and negative 1 if the column player wins. So if the row player throws out one finger and the column player throws out one finger. Oh, by the way, and I'm also going to assume here that the row player is the even player and the column player is the odd player, okay? So row player is even, he throws out one finger. The column player is odd, she throws out one finger. The sum of 1 plus 1 is 2. That's an even number, so therefore the row player wins. On the other hand, if they throw out 1 and 2 fingers, like this position here, where the row player is 1 and the column player throws 2, or vice versa, row player throws 2, column player plays 1. In those cases, the sum is odd, so the column player would win. Okay? So again, very simple game. Once again, it's an anti-symmetric, no, I'm sorry, this one is actually a symmetric matrix, as it turns out. But that also shows that the game, the rules aren't exactly the same in this case for both players, because if the sum of the fingers is odd, the row player wins. If the sum of the fingers, if the sum of the fingers is even, the row player wins. And if the sum of the fingers is odd, the column player wins. So you might say that's an asymmetry in the rules. However, this is still a perfectly fair game. And again, that shows in the fact that in this case the payoff matrix is perfectly symmetric. So if both players, if the players reverse their moves, then the payoffs are the same. In this case, also, you would expect that in the long run, neither player has an advantage. So if both players are competent at playing this simple finger game, then in the long run, neither player will win more often than the other. And therefore, again, we can say the expected value of this game is also 0. So this is an example of a game where the payoff matrix is not anti-symmetric. The rules, in a sense, are not perfectly symmetric, but nevertheless, it's a fair game. Both players have an equal opportunity of winning the game. Now, it's important to note that in both of these two games, the best strategy is simply to move completely at random, to pick your move completely at random. So like in evens and odds, you just throw 1 or 2 fingers completely at random, regardless of whether you're even or odd yourself. You just want to throw your 2 choices completely at random, but with equal probability, right? You want to keep your opponent completely in the dark, or at least as much in the dark as possible about what you're going to do. Because if the opponent knows what you're going to do, then they can exploit that. If the opponent knows that you're more likely to throw a 2 than a 1, then the opponent can use that to try to get the outcome he desires, right? Similarly with rock, paper, scissors, if the opponent thinks you're likely to play rock, he maybe thinks that you just have a fondness for rocks, you're more likely to play rock, then if you're the row player, you're more likely to play rock, then he's going to try to play paper more often, and therefore he'll actually will succeed in beating you in the long run, or winning more often in the long run. So it's a very important and fundamental observation in these kinds of games that you want to keep your opponent guessing. You do not want your opponent to know what you're going to do. And so basically, the best strategy involves choosing your move at random, right, to conceal your strategy from the other player. However, well, in these two games, we not only choose our move at random, but we also choose each move with equal probability, right? So you don't even want to be biased in favor of rock or paper or scissors. You want to play all 3 moves with equal probability, 1/3 of the time. So at random, but with equal probability. And same thing with evens and odds. You want to play 1 and 2 fingers with equal probability, but at random. There are other games that are more subtle, where you might want to, you still have to play your move at random. You have to keep your opponent guessing. You don't want your opponent to know what you're going to play. But it might be better to play some of your moves more often than others, right? Some of the moves might be more beneficial, and it might be better to play them with a greater probability than others. So I'm going to take it as given at this point that we know that the overall strategy in playing these games is to play at random, and what we really have to figure out is what probabilities should we use for playing each of the possible moves, right? In these two games, it turns out that the optimal probabilities are equal, right? You should play each move with equal probability. But more generally, there are lots of games where you actually don't want to do that, and the problem that we'll be solving will be to figure out what probability should we assign to each one of the particular moves. I find that the terminology a little confusing as it's used in game theory. All the basic moves that a player can choose from are called strategies in game theory. And then the mix of strategies, the probabilities you assign to each strategy, is called a mixed strategy. I find that confusing, using the word strategy for both the basic moves that the player can make and also the mix of moves. So I'm just going to use the words moves and mix. So when I refer to moves, I'll be referring to a particular choice that a player can make in a particular play of the game. Like when you're playing evens and odds, you have a choice. You can either play the move 1 or you can play the move 2. If you're playing rock, paper, scissors, you can either play rock or you can play paper or you can play scissors. And the overall mixed strategy in the game is how you mix up those moves. I'm going to refer to as the mix, right? So in rock, paper, scissors, the best mix to use is just to choose each possible move with probability 1/3. And so, as I said, the goal in playing one of these games is to figure out what the optimal mix of moves is, right? What probabilities to use to play each one of the possible moves. And apart from those probabilities, you play completely at random, right? Okay, let's look at a simple example of somebody using actually a flawed strategy in playing a game. Suppose we're playing evens and odds, right? And suppose the even player, again the rogue player, I'll assume the rogue player is always even, suppose the rogue player adopts a mix of strategies of throwing one finger with probability 1/3 and throwing two fingers with probability 2/3, okay? That's not a good idea. As we said, it's not a good idea to favor one over the other. But let's just investigate what happens if the rogue player does this, right? Well, first of all, we can represent that mix of moves with a vector. So we can say it's the vector 1/3, 2/3. 1/3, probably throwing the first move, which is throwing a 1, and 2/3 probably throwing the second move, which is a 2. So I use M for mix, and the little r in the subscript stands for the rogue player. So this is the mix that the rogue player is using. 1/3, 2/3. Right? As I said, it's not a wise strategy. What you can figure out is what happens with that strategy if the column player plays each of her possible moves, right? So, for example, the column player might throw a 1. Suppose the column player does throw a 1, right? Let's take a look back at this. If the column player throws a 1, then the 1/3 of the time the rogue player earns $1, and 2/3 of the time the rogue player loses $1, right? Because he's playing the moves with those probabilities. So therefore, the expected value of the rogue player when the column player plays 1, right? If you just look at those occasions when the column player plays 1, the expected payoff is 1/3 times 1 plus 2/3 times -1. That comes out to be -1/3. So it seems that if the column player just plays 1 all the time, then on average the column player is gonna win like 33 cents on average per play of the game, right? 1/3 of $1 on average per play of the game. So this is not a good mix for the rogue player to use because it's vulnerable to counter mix by the column player, right? Incidentally, notice that this calculation we did here, we multiplied the probability times the payoff for each of the rogue player's possible moves, assuming that the column player was playing 1, right? What that amounts to is the dot product of this mix vector with the first column of P, right? So these are the payoffs when the column player plays her first move. So we take the dot product of this column with the mix vector, right? And that does this calculation for us. It gives us the expected value when for this strategy or for this mix when the column player plays the move 1. If we take the dot product of MR times the second column of the payoff matrix, that will give us the expected payoff when the column player plays her second move. And in that case, if you do the calculation, it comes out to be positive 1/3. So that would be bad for the column player. That would be good for the rogue player because that's a positive payoff, right? So if the column player plays row 2, then chances are the column player is going to lose a third of a dollar on average per play of the game, right? So clearly, the column player is better off just playing a 1 all the time, if the column player knows that the row player has chosen this flawed strategy. Right? Okay, the thing to know here is that when you dot the mix times each column, then you get the expected payoff for each of the column player's moves, right? And therefore, you could actually just take M transpose to take this column vector M and turn it into a row vector and multiply it using matrix multiplication times P, and what you'd get would be the vector of expected payoffs for each one of O's moves, right? when you multiply M transpose times P, you're multiplying M transpose times each column of P in turn. You're basically just taking all those dot products. Note that also we can do the same kind of calculation for any mix that the column player might choose. If the column player chooses a mix, let's say MC, so again, M for mix, C for column. So again, this is some vector that describes the probabilities that the column player is going to use to play each of her possible moves. Then we do the same thing. We would dot the mix MC by each of the rows of P, because now we're looking at it from the other point of view. So we dot M times or MC times the rows of P, and that means we'd just be multiplying P on the left times MC on the right. Right? So the only difference is whether you multiply on the left when you're using a mix for the row player, or multiply on the right when you're using a mix for the column player. And in either case, what you get is a vector of all the expected payoffs for each of the opponent's moves. Okay, so for example, in this case, this result, M sub r transpose times P, that would consist of the row vector that has negative 1/3, 1/3, right? Okay, the last example I want to do is a game called Mora. Actually, Mora is a family of games that I think is believed to go back to the Roman Empire, that the Roman legionnaires used to play this game to settle disputes and maybe just for gambling and things. And there's lots of variants of it. It's another finger-throwing game. You can throw out fingers. And there's all sorts of variants all over the Mediterranean area. Evens and odds is actually an example of a variant of Mora. The variant I'm going to do on this page is a little more complicated than evens odds, but it's a bit simpler than some of the variants that are played. There's actually, if you believe it or not, there's actually a competitive Mora league in Europe, and they have championships and everything and uniforms, so people get together and they play this finger game competitively. In the more complicated version, you can throw out any number of fingers on one hand, like anything from 0 to 5 fingers, and you try to guess what the sum of all the fingers would be. And you may have a whole group of people playing this simultaneously, so the sum could be, any number, into any two-digit number practically. Anyway, I'm going to show you a simpler variant here. This is simple enough that we'll be able to solve it exactly and find the optimal strategy. So in this game, it's like evens and odds in that each player, and there's only 2 players in this game, each player throws out 1 or 2 fingers. But instead of the players having fixed sides, one being even and the other being odd, the players also simultaneously call out either even or odd as they're throwing their fingers. So they make a guess simultaneously as throwing out their fingers of what the sum will be, whether it will be even or odd. Okay, so there's actually, in this case, there's 4 moves that a player can make. They can throw a 1 and call even, and I'll call that move 1E. They can throw a 1 and call odd, right? So they're throwing a 1 and they're predicting that the sum will be odd. They can throw a 2 and call even. I'll call that 2E. Or they can throw a 2 and call odd. And of course, the other player has exactly the same 4 move choices. So here's the payoff matrix. The row player has these 4 moves that row player can play, and the column player has the same 4 moves. So for example, if the row player plays 1E, then we're in the first row, and the second player plays 1O, we're in the second column, then the result is this entry in the first row, second column. That's a payoff for the row player, because the sum of 2 fingers is 2. That's an even number, and therefore the row player who called even wins, whereas the column player called odd definitely did not win, did not guess correctly what the sum would be. Notice that a lot of the payoffs are zero, because if both players call even or if both players call odd, then they either both have guessed right or they both guessed wrong, and so there's no payoff in that case. It's a tie, right? So actually half the payoffs in this payoff matrix are zero, right? Whenever both players guess the same thing. Another thing to note, one other thing, important thing I should notice, the payoff is equal to the total number of fingers. So unlike in rock, paper, scissors and evens and odds, the payoffs aren't just one and negative one. The payoff is equal to the number of fingers that were thrown. So the payoff here was 2 because each player threw one finger, and therefore the sum of the fingers was 2. In this case over here, this is what happens if the first player throws one finger and the second player throws 2 fingers, and the sum of the fingers is odd. Its sum of the fingers is 3, so the payoff is 3, and the payoff actually goes to the column player because in this case the row player called even, and the sum actually was odd. Therefore, the row player did not win. The column player did call odd, so it's the column player who wins, and the payoff to the column player is 3, so I denote that by -3, right? Because again, the payoff is always in terms of the row player. Notice again that this is an anti-symmetric matrix, which again corresponds to the fact that this is a perfectly symmetrical game, that the rules are exactly the same for both players. So if the players exchange their moves, then the payoff will also go the other way, right? So again, anti-symmetric is noticing that a payoff matrix is anti-symmetric is an easy way to note that the game is perfectly fair. The rules are exactly the same for both players. Now, clearly, in this game, again, just as in the previous games we've looked at, you do not want your opponent to know what you're going to play. So if your opponent knows, for example, that you're going to play 1-0, then your opponent can exploit that by playing 1-E, right? If the opponent knows you're going to play 1-0, throw out one finger and guess odd, then he's going to throw out one finger and guess even. And that way he will win $2, right? Because we've thrown out 2 fingers, so the payoff is 2, but your opponent guessed wrong, you guessed right, you guessed even, and you win, right? So basically, for any move that one player makes, the other player can always exploit it if they knew the first player was going to play that move, right? So whenever one player knows what the other player is going to play, they can always exploit that. So, as usual in these games, we want to keep the opponent guessing. We do not want the opponent to know what move we're going to play. So let's try this. Maybe we should use the same strategy that we used before, and we'll just play each of the 4 moves with equal probability, right? That'll keep the opponent in a state of maximal uncertainty as to what we're going to do. So, suppose the row player uses that equally likely outcome mix, right? And he's going to play each move with probability 1/4. So MR, the mix for the row player, is going to be 1/4, 1/4, 1/4, 1/4. Play every move with probability 1/4. Then, as we saw, we can compute the average payoffs for each of the opponent's possible moves by taking the transpose of the mix vector and multiplying it times the payoff matrix P, right? So that's basically just taking the mix matrix and dotting it times each column of the payoff matrix in turn. So if you dot this times the first column, it comes out to be positive 1/4. If you dot this times the second column, it comes out to be negative 1/4. If you dot this times the third column, it also comes out to be negative 1/4. And if you dot it times the fourth column, it comes out to be positive 1/4. So this is the result you get. And the way you read this is that this tells you what the average payoff is going to be whenever the opponent plays one of her 4 possible moves. So when the opponent plays 1E against this mix, right? The row player is always playing moves with these probabilities. Then when a column player plays 1E, the expected payoff is 1/4, so that the row player is going to win $0.25 on average per play of the game. On the other hand, when the column player plays 1-0, then the average payoff is negative 1/4, so the payoff is an average of $0.25 to the column player per play of the game, and so on, right? Now, the thing to note here is that these numbers are not all zeros, right? And that means that the column player could actually exploit this knowledge. If the column player knows that the row player is playing each move with equal probability, then the column player can exploit that by restricting her moves to just 1-0 and 2-E. If the column player just plays those two moves, then on average the column player will win $0.25 per game, right? So it turns out, maybe counterintuitively, that in this case it is not a good strategy to simply play all four moves with equal probability. You have to do something a little more subtle, right? Because if you do this, you're open to being taken to the cleaners by the column player, right? And of course, the same thing goes for the column player. If the column player played each move with equal probability, then the row player could exploit that. So what we'll do in the next video is we'll figure out how to actually compute the optimal mix for each player, and incidentally we'll also show how to compute the expected value of the game, right, which is also an important number to know.